Hello and welcome to 16.4? Yeah, something like that. But this could very well be the last video that you watch of me. I know. Don't cry. You can always rewatch it if you want to. But here we go. We are getting into our trig functions some more. So, model periodic phenomena with trigonometric functions. Mr. Lin, when am I ever going to use this? Well, that's what kind of this whole section is about. It's about taking data and seeing if you can match it to a trig function. If you can do that, then you can predict the future, which is what a lot of mathematics is sometimes all about. And just in case you're wondering, here's Rudy, little Rudy. Say hi, Rudy. Anyway, so I can use sine functions to model periodic phenomenon to solve real-world problems. So when it says periodic, anytime you have something that's going up, down, or back and forth, then a sine or cosine function is probably going to be a really good function. Rudy, go away. The flu. So right now I'm making this during a COVID season, which is not the flu. But the flu, in the same way, well, just like every other year, there's a flu season, right? So healthcares and hospitals have to be prepared. They don't just want to sit on a stockpile of flu vaccines or treatment. So they have to be able to predict the future. And they do that by tracking patient numbers and making a model of it and, predicting the future. And then you can use our trig functions to help do that. So let's just jump right in, right? Here is our situation. It says model periodic phenomena with trigonometric functions. So let's say you have data, because you've collected data, like the last thing we were talking about, like flu patients. Now what do? Do you notice a pattern? Can you fit a formula to it? So that's what we're going to do. So remember, we've got our generic sine function and our generic cosine function. So just make sure you don't forget those. And so here we are, we've got modeling. It's in Washington, D.C. Average monthly high temperatures. So month 1, the average monthly high temperature in degrees Fahrenheit was 42. Month 2, 44, blah, blah, blah. Up into month 6, 83, 87. Wouldn't that be great if that was the high in summer? And then it goes back down. So again, this is through a full year. I'm assuming this is January, February, March, April, May, June, July, so on and so forth. So let's see if we can't match a model to it. So they're giving us a sine. Could we use cosine? Yeah, we could. We just might have to transform a little bit. Either way. So they're recommending that we use a scatter plot to plot the data points and to help determine parameters A, B, H, and K, and blah, 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 blah. The period of a general sine function, don't forget, is 2 pi times B. The period for the given data is 12 months. So we can actually figure out B right now because 12 equals 2 pi B, and therefore we do some algebra, divide 2 pi by both sides, we get B equals 6 over pi. So sometimes using real world data, it makes sense because even if maybe the pattern goes twice in a year, we just might straight up want our period to be a full year. That's not the case in here because it's, like winter and summer, but whatever. So we've got our B equals 6 over pi. All right, I forgot to get my iPad working, so here it is. So we just figured out our b, and we know that our b is equal to 6 over pi. Hey, we are well on our way, right? So here's our scatter plot. So you can kind of see that there is definitely a trend. Something like that. Oh no, oh no, I lost my B. So I think the next step is going to be for us to find either an amplitude or a midline. So first of all, let's remember a B. How does a B transform the graph of a parent function of sine of x? The B deals with, it stretches or compresses the graph horizontally. Yay, good thinking. So the midline for the graph is the first step to finding the amplitude. Typically it's y equals k, and they bring up a really good idea of typically in real world situations where you're trying to find the midline, it's best to just take your maximum value and your minimum value and find the average, or divide it by 2. And then you will find the midline. So in this case, our maximum is 87 degrees, and our minimum is 42 degrees. Divide all that by 2 will give us our halfway point. And in this situation, the average of these two is 64.5. So that means that our midline, or our K, is, we can say, is 64.5. 64.5. Okay. So we've got that. Let's see what questions they have for us. How does the value of k transform the graph? You know what I should do? I should write the generic model on the screen just so we can look at it over and over again. A sine of 1 over b m minus h plus k. The reason that reminded me of that, woo, I have awful handwriting sometimes. The reason that reminded me of it because when I look at the equation, I know that that value is the vertical translation, up or down. Sometimes I forget the letter that goes there, but my brain remembers that that value is it. So that's why I want to write it on the screen for people that are like me. I don't know. Whatever. How does the value of k transform the graph of the parent sine function? It does not. It translates the graph horizontally. Ouch. My bad. I was thinking up and down in my head, but it came out horizontally. My bad. Anyway, the amplitude A is 1/2 the vertical distance between the highest and lowest data points of the scatter plot. So A is equal to the average. Oops. Go away. So this is what we did to get the average. So A is 1/2 the vertical distance. Yeah, so how is that different than what we did for the average? Let's scroll up here real quick. So our average was like right here, and our amplitude is that distance and or that distance. If it's a good average, it would be the same. Okay, so there's our average. I was just double checking on that. Oh, so the average is you add those two values together and divide by 2. The amplitude is you find the difference of those two values and then you divide that by 2. So I wanted to take a minute to make sure that I explained that correctly so we understood that mathematically that's what we're doing. Again, oops, we've got our graph, we've got our midpoint, our amplitude is that distance, so we can take our maximum minus our minimum, that will give us this full distance, and then divide that by 2. Whereas the average will give us the actual value of that midline. So try to keep that straight in your head. So we found the amplitude. We took 87 minus 41 and divided by 2, and that's going to equal 22.5. So you see what we're doing? We're finding all of the parameters so that we can figure this out. So the graph of a general sine function crosses its midline at x equals h. The first time the temperature passes 64.5 degrees is during month 4. So h is approximately equal to 4. So now we have h equals 4. So again, that's one of those things where you can either look at the parent function and kind of compare with what we've got here, or you can remember some of this algebra stuff to help you figure that out as well. So now we've got, let's see, we've got A, we've got B, we've got K and H. All we're missing is this M, but we can substitute the values in for each parameter. The model is, oh, we don't have to solve for M. M is the month that we're in. Okay, that makes sense. So then we've got our equation right here. So we literally just took all of these things, plugged it into that, and that's what we got. Make sense? What can you do to determine how well the model fits the data? You can always graph the model and then compare it to the actual data. I wonder what they were looking for. Using a graphing calculator. Hey, look at that. How could you use the maximum and How could you use the maximum on the scatter plot to write a cosine function to the model of the situation? So you would go through the same thing, except whenever we are figuring out our h and k, so those are going to be slightly different because the cosine function, the parent function, starts and stops at a different spot. So you could model this with a cosine function, but your h and k are going to be different. Your amplitude and your period would still be the same, but it would be transformed a little bit different. That's all. Okay, so we did model periodic phenomenon with trigonometric function without using technology. Guess what we're going to do this time? We're going to use technology. So we've got the same problem that we went over, but this time we're going to use our graphing calculator to help us out. So again, this is most likely more like what you would do in the real world if you're ever going to use something like this. You would have data, and it would be on you to kind of see that there is a relationship and maybe make a good prediction about which relationship you should use. But then you'd have a computer kind of figure out the rest of it. So we're going to pull up our calculator. And this is just like whenever we did the exponential regressive functions on our calculator. It's the same process. So if you remember, we started with stat. And we're going to edit. This is where we edit the lists. And this is where we're going to enter our data. So your list 1, your L1, is going to be like your X value, or in this case, the months. I already went through and added all of the data because I figured you probably didn't want to sit there and watch me enter data. But list 2 is going to be your average high degree temperature from your data. And then you'll see that we go all the way through. So to look at it, step 1, you probably want to look at your window. So I set my X minimum to 0 because I can't have a negative number of months. I set my X maximum to 12 because we're only doing our full period is 12 months. Scales 1. So our Y minimum, it was set at -1. I just left it. I didn't care. And I put my Y maximum at 100 because I knew that it didn't go over 100 degrees, and I wanted the graph to be kind of in the middle. So we push our graph, and so there is our data. So from that, we can definitely see that, oh, that might be, a sine or cosine function. In this case, we're going to do it as a sine function. So now let's make the calculator do that for us. Do you remember how? So we're going to go back to stat. By the way, I should back up. So whenever you push the graph, if you don't see these and you did change your window, then you'll need to go to stat plot and turn your plot on. So notice how plot 1 is on, plot 2 is off. So to turn it on, just select it, and then you can again select which list you use. You can change the type of mark that you want to use, and then the color. For those of you with fancy calculators. I didn't have fancy calculators when I was growing up. Back in my day. So I changed a couple things. Boom, there it is. So same data. Okay, so we want the calculator to come up with a function for us. So again, we're going to go back into stat, but this time we need the calculator to calculate something, right? So we're going to push the right arrow button until this calculate button is selected. And then we're just going to go down. So again, here's our linear regression, our quadratic, cubic, quartic, blah, 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 blah. There's our exponential regression that we used earlier. There's a logistic. So then there's sine regression. What is this? Go away. So that's one we want to select. It's going to use list 1 as your X list. Your Y list is going to be list 2. You can leave the iterations as 3. You can enter some of this stuff in, but I just push calculate, and so it gives us a bunch of stuff. So take note. So if we look at these values and compare it with what they got in the book, blah, 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 blah. So this is what they got. It is very similar, but not the same. So notice how they have a negative number here. We have a positive number, but it is the same number. But also the thing that I wanted to point out to you is their version gives you, this is their generic function right here. So then when they say b equals this, that's 1 over b. Ours, and I'm sure there's a way to change this, but I don't know how to do it. So I'll just do it with math because I like math. ours does not have a 1 over b on the outside here. It put the b on the inside with the x term. So how would we make this look like the one that's in the book? And the reason I'm going through this is because if you have any problems like this on our homework or on our practice work, we're probably going to have to do that. So to take this out of the parentheses, as long as we keep everything inside of the sign, we can just do normal algebra on it. So to move this out, we would just divide both of these by b, this number, and then we can just pull it out. So what that means is, to make this look like the way they have it in the book, let's see here, where's my little... So what they want is they want a, f of t is equal to a sine of 1 over b m plus, what letter did, k, h, k, no, 8. Oh, I don't remember. They use C, whatever, doesn't matter. We'll say C plus D, right? Sorry, I'm at the side of the screen there, but whatever, we'll figure it out. So to make ours look like that, so what we have is our A is 22.83 sine of 1 over B, shoot. Let's see here. So we have 0.51 x plus or minus 2.06 plus 64.2. Again, sorry, I'm running out of room. So to pull this thing out, you would just have to divide both numbers by that number. So what you would do is take 0.51, and then we'd take 2.06 divided by 0.51, and then we can rewrite it as, and I'm going to round even more because I don't want to write, 1 over 0.51, which is gross, I admit, but whatever, x minus, and then you could stick that in your calculator, whatever that would equal. That number would go there, and then you'd be good to go. So again, this sine function, though, applies to that whole thing, which is why we can do it. We didn't pull anything out of the trig function. We just rearranged it so that it looked like the form that we wanted. So be aware of that. Solve a real-world problem using a sine model. So you can use the graph of the sine function model to identify values of interest. Okay. So the table shown displays the average daily amount of daylight in hours of Washington, D.C. for each month of the year. Cool, we have a data point. For what days of the year does Washington, D.C. receive at least 12 hours of daylight? So let's see here. We let M1 represent January, M2 represent February, so on. Enter the data into a graphing calculator and use a sine regression feature to find a model. Okay, so entered it into the calculator, found a model, and then plug that model back in so we have a line there along with our data points. And so the question is, for what days of the year does Washington, D.C. receive at least 12 hours of daylight? So if you look, the y-axis is telling us hours of daylight, we can draw this line here and figure out that everything above this line receives at least, if not more than 12 hours of daylight. Everything below does not. So why is the graph of D equals 12 included? Because that's the graph that, or that's the line that we're looking for everything above it. Let's see here. Complete the sentence. The portion of the sine curve that is above the horizontal line represents all the days of the year when Washington, D.C. receives more than 12 hours of daylight. What is the significance of the points where the curve and the dashed line intersect? Let's see, they represent endpoints of the full period. No. They can be used to find the amplitude of the sine. We don't necessarily know that, although it kind of looks like it's in the middle. They represent the 2 days when there is approximately 12 hours of daylight. I'll agree to that one. And then M. So Washington, D.C. gets at least 12 hours of daylight from about March 17th to September 24th. So that's what they're doing up here. So they're using that first point. Let's see here, M equals 3.076, which the third month is January, February, March. I'm bad at months. And then 0.7631 is 2 days after March 15th or March 17th. Why does that matter? 3.076. So I guess they're saying that 3.3 would I guess be March 1st, and 0.76. Is that what they're saying? Let's. So as we look, I guess this is the average. Oh, here we go. Let M equals 1 represent January 15th. M equals 2 represent February. So when we come down here, that's what I get for not reading all the way through. So M equals 3 represents March 15th. M equals 3.076 is approximately 2 days after March 15th, so that's 17th. And so you can find that by just doing a quick ratio of there are 31 days in every one of these, so that's why they just times it here by 31. Or I guess there's 31 days in March. Same thing down here. There's 30 days in September, which I would have to look that up because I don't remember that stuff off the top of my head. But so you can use that data to then answer this question. And that, I believe, is our last task. So, try out the check on learning. If you're having troubles with that, I'll see you in the next video.